Hello everyone, my name is Nadav, Nadav Voloch. First of all, let me thank Professor Mastorakis, I hope I'm pronouncing the name correctly, and all of the committee to allow me to participate remotely from Israel. And as you know, the situation here is not, it's very hard. So I thank you for allowing me to participate remotely. This is actually a good distraction from the current situation. This research, as you can see, is called the multiple subset problem as an encryption scheme for communication. I'm going to explain about the name, even if some people are not from this field. I'll try to make it as clear as possible. It's part of the prepared presentation. And this is research done by 4 of us from 2 academic institutes here in Israel, the Rupin Academic Center and Ahva Academic College. And the main collaborators are Dr. Zadok, Dr. Bloch, and Maor Hajaj. So I'll just begin. So usually I'm beginning a little bit about what's encryption generally, and usually encryption is done by using well-known mathematical problems. So encryption is usually widely used technique because they're usually computationally hard and provide the actual there's the actual just hold on 1 second. Okay, so usually the using well-known mathematical problems for encryption is a widely used technique because our goal in encryption is to find something that is very computationally hard to find for the encryption to be a good encryption, and thus providing security against potential attacks on the encryption method. One of these problems is called the SSP, the subset sum problem, and I'll define it very simply, like the basic, very basic and simple problem. If we have a given set, as we can see here, A, that has the items here, in this case, are integers, 3, 4, 5, and 11, and a given integer S, let's say it's 15, that we want to actually see if the items can sum up to this number, to the sum. So if it's, for example, S15, the answer is of course 2 because we can divide S15 by 11 plus 4. But if we have a given integer of 17, for example, we can easily see that the answer is false. You can't divide, you can't sum up these items, any of them, some of them, even one of them, you can't sum them up to 17. You can see and try, you can take 11 and 4 and 3, and it's 18. So it's not possible. All of the possibilities are can't sum up to 17. So we have a set of items, and we want to see if they can sum up to a certain number, the sum. So this is the basic, very simple problem of subset sum. And in this research and this encryption method that we here, we take another version of this problem. It's called the multiple subset problem, and we take not just one set. We're taking here a set of sets, meaning a 2-dimensional set that is devised from several sets, and that we, instead of taking known sum, known number, we want to try and find in those sets if such a number exists. Meaning, if we can devise a certain sum, it will be the same sum for all of these sets. We can achieve it. We'll see a relatively simple example in the next slide. This problem is NP-complete because we consider it a variant of the subset sum problem, and it's even more complex. but there's actually an algorithm that is relatively efficient for if we have no private keys or explained by the private keys. And this algorithm is actually based on dispensing the non-relevant values of potential sums, meaning that if we see that we have the maximal sum, I'm just, we have, I don't know, 100, 200, 300, 400, and it's the largest sum, the others are, I don't know, tens. So if we don't have a point of searching for sums that are larger than this sum, because it obviously can't be reachable by the other sets. Same goes for the minimal ones. So if we actually do the limits for this specific set, it comes out pretty efficient because we don't have to look that much for the sum. And in this specific research, we further developed the encryption scheme that we began investigating several years ago, 2017 to be exact. And we had the paper published. It was the first paper that established the beginning of this research. And there's a link in the references here and also the paper. And so, as I said before, here's an example of the multiple integrated subset sum problem as an abbreviation for MISSP. And as I said before, our goal is to actually reach a certain number. It could be reached, it could not be reached, we don't know. We're checking. That's what the algorithm checks. And we can see an example. We have here a 2D set A that is consistent of the sets A1, A2, and A3. We can see the set items here. We can see that A1 is 22, 4, 23, 16. And here we have A2 that's A3, 17, 21, and A3 is 18, 13, 9, and 19. So we want to find out if there is such a sum that is reachable by all these sets. And in this specific case, there is 49, and here are the summations of every set specifically. The thing is that it's not necessarily you can reach such a sum. For example, if we take the 2D set 3B, we can see that no such sum exists. We can't reach the same sum by all of these sets. It's not possible. And there are some cases, usually with small scale numbers, that we don't get a singular answer. We can get, usually it's 2, maybe 3, could be more, but the probability is not that high. Here we can see an example that 2 solutions exist. That you can see here in C, we have 8, 15, 11, 9, and 1. And C2, we have 13, 2, 7, and 1. And C3, we have 18, 11, 10, and 19. And there are 2 possible sums, 10 and 21. And these are these calculations. We are specifically interested for the encryption purpose in the singularity case, that there's only one solution. It's important because we'll see the encryption process in a minute. So the classic subset sum cryptography, known as the Merkle-Hellman-Knapsack cryptosystem, the reference there, was the first one created with the subset sum problem. It was actually derived from an knapsack problem with SSP. As a special case, there was a paper that actually investigates this issue. The fundamental crypto system relies on constructing super increased sets, which the number is larger than the sum of the all preceding numbers. Specifically, the subset sum problem was then solved by a greedy polynomial time algorithm. There's also a reference there of the research that does that. But this specific crypto system was later compromised, and then it was developed like more intricate versions of a subset sum problem for getting a stronger crypto systems that we can see in 5. And so in this context, we propose here a utilization of the MISSP as a relatively robust crypto system with private keys that we'll see in a second. So For those who are not in the field, I'm going to explain just a little bit about what's encryption in general and what's specifically symmetric encryption. When we talk about symmetric encryption, we refer to the private keys, and I'll explain in a second what keys mean. And in really the basic simple definition about symmetric and asymmetric encryptions is that in a symmetric crypto system, the private key of the encryption is the same as the private key of the encryption. It means we use one key or two keys, but the same keys to encrypt and decrypt. And in an asymmetric encryption, it's different keys for encryption and decryption. But we're not talking about that now. In specifically how symmetric encryption works, is that we have a message. This message is the message that we want to deliver to someone, and we want it not to be found by any other third party. So we take this message, for example, is live long and prosper, and we do a certain process that is called encryption. It's an algorithm that includes key, which is basically a secret that only the person who sends the message and the person who receives the message has this key. You can imagine it's like a password or something. It doesn't matter, but it's that's a private information. And with this key, the actual text is encrypted. The actual text is plain text, and it's encrypted into text that if you see it doesn't mean anything to you. It's like gibberish, it's like something, a mumble. As you can see, it could be just random letters that you can't figure out what it means. And this is called ciphertext, the encrypted ciphertext. And the reverse process, if you want to decipher this ciphertext, you use the same key in symmetric encryption. And with this key and algorithm, of course, you convert the ciphertext into plain text, into the message that was originally received. So this is basically the scheme of the process. So the thing is with our specific encryption, MSSP, we have several limitations that will be explained now. It's a cryptographic application for it has to have equal sizes of sets. And the size of sets is denoted here as M, from which we actually derive the number of sets N and an equal number of digits of every integer in the sets T. In this particular application, the ciphertext refers to the series provided sets, and the private symmetric keys are the parameters M, N, and D, which we have to choose two of them. It doesn't matter which ones. The encrypted plain text is represented by the sum S obtained from these parameters. To ensure an accurate decryption of the ciphertext, we must, that's another limitation, we have to have singular results. I mentioned this before. We can't have multiple results because then we won't know what the plain text is. And of course, we can't have the situation that we have no possible sums because it's then we won't have the plain text. And now we can see an example of it. So in this example, we can see the ciphertext is a random set of digits. It's like a very large number. And then we use the private keys. The first private key that we have is Kn, the parameter N4. It means that this large number, it is consisted of several digits. We don't know yet how many digits, and it doesn't still matter. And it means that we have to divide this large number into 4 parts, and these parts are the sets. So all we have to do now is to take the second private key, for example, here it's 2 and it's D, meaning all of the numbers in our items are 2 digits. So now we have the sets, and we also have the number of digits, so we can find the items. Okay, so we can see it's 45, 49, 54, 58, and we actually create, as we can see here, a 2D set, a set of sets. And on this set of sets, as you can see, we do the MISSP algorithm, and we try to find a sum that will be reachable from all of these sets. This specific sum, if it exists, of course, is the plain text. And this is the actual decryption. If we want to see the reverse process of the same data, you can see here 112 is the actual plain text, and we have the number of digits and the number of sets, and we can see that we divide it from there, and we can create the encryption and get to this number. This is the reverse process of encryption. Here we can see several examples of the MISSP decryption. We can see, again, that we're talking about very large numbers. This is actually what makes the scheme more robust. And we can see here that there's a large number, and we have the N and D, and the N, as I said, is the number of sets. You can see that there are 4 sets here. 11 is the number of items in the set. You can see that we have 11 items in each set. And D, of course, is the number of digits. So we have 4-digit numbers, and we have 4 sets. And you can see that the only sum that is reachable by all of these sets is 26,931. And these are the calculations of each set, how you can reach the actual plain text and decipher this ciphertext. There's another example here of a number, again, with 4 sets. And the number of items here is 9, and digits is 3 digit numbers. And you can see that the plain text 2942 is the only one reachable by these items. Okay, so this is the process of encryption to encryption. So this is the basic encryption scheme, and specifically in this research, we also applied it to communication protocol. And for the that's exactly what we did to incorporate the actual modern form of encryption that is based on this mechanism, and it performs the actual encryption and decryption based on the MISSP algorithm. The app technologically is installed on a client's endpoint. It actually enables loading the relevant files, dictionary, keys, data files, everything, and then selecting decryption or encryption operation. When the desired operation is complete, then it's possible to send the file created through the network with this encryption. So our implementation was done, it was a long project. It was done based on Visual Studio and C#, and the actual communication was done in VirtualBox, 2 machines, 1 receiver, 1 sender. And we achieved the fully operational application, displays all relevant data, sends and receives data, and accepts the user preferences. The code itself, we uploaded to GitHub, and there's even a link here and also in the paper to our Git project. And the implementation itself, we had to actually devise a dictionary that will include all of the ciphertext and plain text possible, to making the actual application easier to handle for the purpose of encryption. So if we want to see the technological architecture of the system, this is basically it. We have 4 main classes. The encryption class and the decryption class, I think, are self-explanatory. We need 1 class for the encryption that includes the algorithm, the keys, and everything, and a very similar class for decryption that includes almost the same things, but the algorithm is, of course, a little bit different. And we have a dictionary class that includes lists of signs, and 1 class is actually sign to code the actual number, to actually translate it into ASCII characters, and thus being able to create an actual verbal message in English. So this is the basic technological scheme of the system. As a for conclusion, this specific research introduced the problem of finding the common subsets of intermediate set, MISSP. The objective was to actually identify a sum that can be achieved by all sets with sets if such exists. And we additionally built a robust crypto system using symmetric private keys was identified, and we implemented it in a communication application as I just explained. That was also discussed. Last but not least, for future work, ongoing work, it's actually current ongoing work. We want to actually improve the MISSP encryption algorithm because ever since 2017, there have been newer results. I put several references from actually Greek mathematician Aris Pamaglosis, I think. So I'm sorry if I'm not pronouncing it right. And we used a lot of his mathematical methods for the problem to implement our algorithm, and he published newer and more efficient results. So we want to improve also our implementation and our algorithm using his methods. These are the relevant researchers, and even in the first paper, we also cited his mathematical scheme. We're also trying to combine the encryption algorithm in non-standard protocols like Bloch and stuff like that, such as Tor. Onion mounting, if anybody knows, we did it in another problem and solving existing problems with. There's also a reference to a paper we published last year on the topic. And the last interesting aspect of this research is actually trying to analyze attack scenarios on this encryption to test the strength to see how actually strong the scheme is. So maybe we can try and attack it with different methods and see how robust it is. This is it about ongoing work. And some acknowledgements. Of course, I want to thank again to the committee for allowing me to participate remotely. I wish to acknowledge also our students, Phil Zevi and Nadav that did an amazing work in the implementation, in building the code, and Whoopin Academic Center were supported with students and financially this entire research, and Afba Academic College also that supported financially this research in all of its stages, and that's about it. If you have, these are the references I talked about. I won't go over all of them. The first one is the first paper. Actually, I published it by myself in 2017, and it was the beginning of the research. And we have here 789, the newer research paper that have better mathematical methods. And the last one is our research from last year, from 2022, about the Tor encryption. And in 6.6, you have the link to our Git project of the code itself, of all the implementation of the crypto system. I'm not physically there to answer questions. I want to thank you for your attention, and you can email me or approach me if you want about questions on these methods. I'll be more than happy to answer. So thank you very much, and hoping for better in 5 days. Thank you.